Okay. Can you click on? You have the mouse somewhere under pizza.
There's nothing.
And remove this
thing
as well. You can minimize it.
Why don't we have a microphone like that in the other rooms?
Because Brad made me buy it, practically. Because the
So we're pushing the wrong person.
No, push pins. No, it's we have. I'm not the center director. We have the center director who's in charge. Yeah, things like that.
Oh yeah, sorry, inside joke.
Yeah. But okay, Yaorong has finally gotten ready to present the fantastic discoveries that he made during his PhD that he was hiding from us for so many years. But now they're ready to go, and this is a presentation for the proposal, preparation for the proposal. Anyone who is able to critique and comment, especially people online, please do. Rogers here is one of the committee members. He's not expected here, but yeah, because we thought we will make the presentation so that committee only sees the final version. But anyways, everyone is welcome. No, I'm just joking.
You know what I'm doing.
Yeah.
You know everything.
But still, presentation.
Yeah.
So let's start with it. How will you propose?
Okay. Thanks everyone for coming, and I will practice my proposal with 6 days advance. Please stop me at any moment for the slides or contents or anything unclear. I probably make some wrong comments because all of the research idea is inspired by some my brainstorm during all the way from the beginning. So the title is an adaptive data batching strategy for enhanced representation learning. So two main points. One is the batching strategy. Another one for representation learning. It will cover blind source separation, ICA, and some further application on representation learnings. And this is why I gave this title here. So the contents, I will not cover. I will not go like many contents, but I will spend some time on intuition and background, how I get this idea, how I found the way to get this baseline model. And then I will give some relative explicit explanation of the model I found it, and how it's applied it, how the experiment do, and then give some stretch goals based on the baseline model I found it. How can we apply it further, like for self-supervised learning, federated work, or some recent of my project, like for the hyperspectrum image reconstruction. And then we'll come for any question at the end. So how I start off all of the things, like from 2-3 years ago, I kind of started working on the topic independent component analysis. So what it does is, we all know, I think we all at least heard of a cocktail party problem. Is that we have a list of sensors, let's say two sensors, and two random people speaking in this room, and both of the sensors will collect the audio information from both speakers. But what the audio got is a mixture of the speaker. So what we want the individual output. So we want to know speaker one, what the speaker one talk, and what the speaker two talk. So the blind source separation method invented out, and they can use of different kind of magics to separate them out. And one of the most widely used method is independent component analysis, called ICA. So one of the key assumption from ICA is independent assumption. So what independent here means, like they assume that each of the speaker, what the audio from each of the speaker is independent to each other. So I did a lot of experiment on images, audios, anything, and trying different objective function. But finally, one time I realized why we have to have this independence.
So, can you define independent, or are you going to make it later?
Oh yes, I will make it later.
You probably say statistically independent, which is important because it could be linearly independent.
Okay, yeah, I was just thinking if I see here people. Okay, yes, cannot.
No,
I cannot assume that.
don't
I
assume.
cannot assume
Just
that.
I don't remember how it exactly works. So that's,
I should have a note. Yes. Okay. So the independent here is in statistic independence. So, but why is independent? Is because so when we say independence, it should be okay. Yeah. So let me think. So why is independent here? And then I came out of some of the problem. Assumption of independence is globally and potentially omit the local data structure. So when you're trying to separate the component, you are thinking that the entire data are independent to each other. But sometimes this is not true. But it's not true. It's true. But when we have limited data samples, you cannot say they are exactly independent, or you cannot use independence because they can potentially have strong correlations. And also, this is what I mean for data limitation. When the data sample is limited, you cannot say they are exact independence. Like we can say two persons are independent, but we have nose, we have eyes, we still have some correlation in this scenario. And also for the computation cost, when trying to evaluate the independence, you have to compute generally higher order statistics or evaluate mutual information entropy stuff. So these are considered to be very difficult to compute and will be very computation expensive, and sometimes it will be time consuming. So based on this problem, then I was talking about the independent, but I'm not trying to explicitly explain what independent is. I'm trying to think of what I got of thinking of this independent stuff. But before that, what is independent? Statistical independence. It means that observing one variable provides no information about the others. So, which means that for here, so everything we consider is generated from some random samples. Like we have a group of samples, and this sample is also generated from some other big samples. And these samples are here. You can randomly pick it and combine it. This precise, I would think I would consider is independent precise. So this is the histogram of the middle images. And there are a total of 256 by 256 samples. So these samples can have a histogram like that, but how you combine each samples can be totally different. They are uncountable. There are a lot of different kind of combination. The first one is also generated from this histogram. Is by visually looking at it, it's just some noise. But indeed, it's like the super Gaussian distribution. And also the second one is kind of a shifted image of the middle one. It still have the same distribution. But we can see that the correlation between the first two is very low. We consider it close to zero. And we can say that they're uncorrelated or to some extent. But when you try and have the second one, they do have some correlations. But the generation process is completely independent because there is a chance that you can have these images from this distribution. Even the first noise-like one is unique. So I was thinking that since this kind of correlation can exist, can we use such of things to do the separation problem? And then I want to talk about the correlation. Generally, people will talk correlation first and then independence, but I do the inverse one because for this whole research is based on second-order statistics. And people generally would think independence is stronger than correlation. But do they? As we know that there is a method called principal component analysis, which can completely remove the second-order statistics, and we use it a lot for pre-processing for different kind of works like ICA. And for this is one of the classic variables for X and Y. They kind of have this nonlinear relationships. But for second order, if you're just using second order to evaluate it, you cannot find in this correlation, even if their correlation is already zero. But for higher order correlations, you cannot evaluate. So Also, I have this one.
So I have a question.
Yes.
Where does random variable x and random variable y come from? Is that randomly generated, or
Definitely not randomly.
is it from like a baseline data set?
I just copied this image from internet. There is some, I think it's the cosine sine stuff. It's not random generated, so
Okay.
it should be from somewhere.
I see, but like is that curve data dependent, or because like
They are dependent for sure. You can see the curve, but they're uncorrelated. So their
if
correlation is zero.
If they're uncorrelated, then you see this curve.
Yes.
Okay.
Okay.
Could you clarify what you mean by want work?
What?
What do you mean by want work?
Oh. PCA cannot found the relation of x, y, higher order relation.
I guess PCA can separate linear stuff, but not something like this.
Even linear stuff, they probably cannot. It's just the second order, so just a correlation.
If it could, what would it look like?
With this example.
Okay. This is to probably just rotate somewhere.
It would still be. I mean, I understand.
Yeah, I know.
You run PCA on this data, it looked different than PCA on that data, and it became that. Gave you that as enough.
The example is not visual. Like, we're not getting the example. That's the point. It's like, what would, because you don't even like tell us the result should be this. What should the result be? No idea.
Oh, should be at least two
But
images.
PCA
What is a mixture and what is a PCA result?
Well, at least how else we understand. It's
Yeah.
like, what does it mean doesn't work? It's a parabola. Here, what are you expecting to get, and what does PCA actually get? So this is not an example where this is clear.
Okay.
I think that's the point.
In the case of an image, I'm not even sure how you would show that PCA does find something related to variance, covariance, and so on and so forth. Like how would that even be visualized? So that's kind of a challenge in itself.
No, I get faces. That's very easy.
Is that second order? Okay.
Yeah, maybe if you start with that at the very beginning, that'd be good.
Yes,
Like as an example, just to like.
I can feel the order kind of
Yeah.
confused.
Like what a first order correlation might look like between two data points, second order, so on.
Second.
Only second order?
For my work,
What
it's
is-
only
yeah,
second
okay.
order. Okay. I'm sorry, I think I forgot why I put the things here. I haven't practiced it.
That's the point of the
Yeah.
session.
In the case of PCA, just be careful, because it's looking for the direction of largest variability. And here you have a two-dimensional grid, basically. The direction of largest variability is probably diagonal. I don't know. I would guess.
Yes, I
So
can see.
my guess is if you run PCA on that thing as it's shown, you would get a vector, and the projection of that vector would look weird. But it's a vector that is not aligned with X nor Y, probably.
Yeah, but this is not a good example, I think, of failure. Of
Yeah, I will
PCA.
change. I will change this.
Can I say something else? I don't know if I'm allowed to. On the very first slide, you had a bunch of acronyms, but none of them were defined. And then,
This one?
yeah, just like small things. As a person I'm new, so I don't really know this topic very well. But,
Yeah.
No,
But just for
they're
clarifying,
there, right? Line source separation, event
the one
command.
before this, the one
Huh?
before this, right?
Yeah,
Yeah,
that's-
they're just like they're all over the place, and I don't know what they mean, and it's just kind of confusing in the beginning.
Mhm.
Maybe even put that after or something.
Okay.
Like if you just move the slide later. Yeah, it also
JD
works.
is clear, but maybe you can say X stands for batches. Does it stand for batches or something else? Your JDX.
Yeah.
JD is clear. What is X? People may not know. When you say all
Don't give it away.
structured batches, does X stand for batches?
So X is Dr. Please give the name at the beginning is my last name. X. That's why I don't want to mention
Say
that.
that.
It's my last name initial.
I mean,
But it's X. Then I think okay, X is fine. It's at least it's
you
not.
have to have a name.
Yeah, then you should clearly say
X is variable. Then it's fine. But I think it's okay. I cannot change the name. It already
don't
exists
change the name.
everywhere.
And also X stands for unknown for anything. This is a flexible method, right?
Mhm.
You can change how you're doing the patching and
Yeah.
and everything, and it's a meta algorithm in a sense. So that's why X fits.
Structure.
Extra. Yeah.
Instruction. Okay, already a lot of problem.
Oh, and then this last one, can you go back here? I still don't get this. Like, I understand that the right ones are correlated, but what am I looking at on the left? What is the distribution of?
It's the same distribution.
Yeah, it's just actually the left one is generated from the middle images. This is how we call it.
All three of them have the same distribution.
Yes, and they have the three.
Uh-huh.
We have a bunch of pixels, and I can align them like anyway, but it's generated from the middle one.
Did you use them? Did you use that?
No, I don't think so. The ideas are
You can make the graph bigger.
what do you call it? Public domain.
What?
You can make the graph bigger.
Yeah, the background should also be changed. I can see.
Yeah. So TJ suggests let's get to the meat. Yeah, because we're diverging.
Okay. Yeah. So Discord. Okay. I think everything at this stuff should be changed. But
save notes for the end for the tiny things.
Thank you. I cannot
you can write
make
down.
notes
You
right
can just slug them.
Yeah.
Yeah. And so let's talking about the batch and strategy. So still I'm using the concrete image as example here. So this one is 256 by 256 images, and the histogram I have shown before. So when you do machine learning training or any deep learning trainings, you do batch, random batch, sequential batch. What I do here, I still looking at this two kind of batching strategy. We can do like a random batch, it is used for most deep learning training. But for here, what I mean, you got these images, you randomly pick pixels from it. Suppose we have picked 32 by 32 pixels from it. It's just randomly pick from the entire images. And you have this one is more like some noise, but it's picked from it. You can see that the distribution of it has a similar trends as that one. But when trying to pick a structured mini batch, what I mean structure is like a small square. It can be from anywhere in these images but a square. I will add a notation. Yes, but for this one, it's probably somewhere here. But we can, because it's a dark region, I think it's on the concrete. In this scenario, you can see that the histogram is completely different to that one. So I would think in that sense, we consider this one is like an independent. It's when we're trying to do blend source separation, you will have a. Okay, I confused myself. So what I want to talk is when we have these images, even if it follows some distribution, but at the localized region, it may not follow that distribution. So then when you're trying to assume that this components, because like for most of the ICA algorithm, like Informax, Fast ICA, especially Informax, they're trying to separate components into super Gaussian. But when this localized batch does not fall in that stuff, well, in that stuff, it will. Okay, sorry. I think I would try another way to talk about this. It's just Yes, for this batch is yeah, I remember. For the batch stuff here, it will provide some of other information. It's not like how the distribution of the components looks like. So because everything, even this images 200 by 200 is still a smaller size of the entire data. If it's generated from a sample, because if it's a distribution, it will be infinite sample, but here it's still limited, and it will have this kind of distribution. Still, you have this smaller distribution, smaller sample size, it still have similar distribution, but this kind of subset is has a chance to exist like the smaller batch. It will have some different distribution compared with other batch, compared with the global one. So why I'm talking about the batching one? Here is the thing. So when you're trying to separating them, so there was not just only one component. There can be exist two or more components. Here's the example. If you have these two samples, I would say two components, they both have 256, 256, and the correlation between them are very low. Let's just say they are nearly uncorrelated. But when you're trying to random mini batch, still random picking pixels from first one, you get the first sub batch, and also the second one, you get the sub batch. And the index of each pixels are fixed, which means if I pick this pixels, and it will also exist in the second one. So they have the same location, and the correlations will be still very low. But when trying to picking the structured mini batch, like this one here, but the second one here, they have highly structured, and you can see that the correlation is not exactly low as that. And this is just a random pick. If you pick others, it can sometimes above 0.2 or 0.3 or still very low.
Are they selected at exactly the same location?
Yeah.
Here?
Yes.
Okay. So it's the location grid is the
Yes.
same under each other, whatever. Okay.
I will put a notation.
Yeah,
yes,
yeah.
I realize that.
Okay.
I realize that. Yes, and the correlation will become higher. So I was thinking, can we find a way to using this kind of feature? So when we have it, we know that these two kind of data are independent or uncorrelated, but we know that in the small interval or small batch regions, they probably have some correlation, or they probably have some other features if we can use of them. So then I put out this question, structured, random, if we can using on these batches to solve kind of blind source separator problem, and also the random batches, if since each of the smallest batches can reflect some of the global features, can we use them to solve like the global or IC problem or make some further usage? And also more things, all of this idea is based on second order statistic. Is that enough for evaluating the whole higher order relations? So my aims for this proposal, I listed 4 points here. The first one is the JDX. So first one is JDX, which has already been proposed and submitted under review. And this work is relied on the structured batch I mentioned, and also the second one, GDRX, is based on the random batch strategy. It's more like a ISA problem, ISA algorithm. And then I will try to talking about the strategy goals for this work on like self-supervised learning or some real application on like federated application or the or the spectrum reconstruction, the hyperspectrum image reconstruction. So these are my 4 aims, at least here. And I will start talking explicitly the detail, not exactly detail of the proposed method. And the first one, the JDX, I would call it joint diagonalization on structured batches. X is still it stands for some variant notation, and it's a second order statistic only, and it's computation very efficient because it relies on the joint diagonalization algorithm. And there's no independent assumptions and no distribution assumptions of the data either, but it do have some structural reliability. I relies on the data. I will talk about that. And the joint diagonalization, a quick go through that. It's refers to to a problem of finding a single linear transformation W that makes collection of matrix as diagonal as possible simultaneously. For instance, you have a list of this matrix. Generally, it's a square matrices. You will find the transformation W that can approximately diagonal each of them simultaneously. So the goal is finding this W to diagonalize all of them, approximate diagonal. So this is what joint diagonalization trying to do. And I will use this algorithm to solve my problem because my algorithm is very straightforward and easy application. Because everything is based on the intuition and application. So here's the.
No, true. You have a theory to prove it. A theorem. You're kind of demeaning your work by saying that. It's simple and easy to run, but it's not like straightforward and blah blah blah. Like, I don't know. We need to say it differently. Like
Elegant.
Elegant is self.
Aggrandizing?
Yeah, aggrandizing. So, but yeah, it is. It's yeah. I don't know. Well, let's think about it because it's not just an application.
Yes.
You have a theorem. You have a proof why it works, right? Proof of efficiency, that etc. So don't demean your work.
Okay. Yes. This is a baseline application of this algorithm. Just using images, some jellyfish images as an example, because this is all the way from my starting experiment. So suppose you have a stack of images, let's say D images of jellyfish or any kind, but jellyfish here, and you got a random linear mixture. You can random Gaussian generate it, and you got to observe the mixture. And then comes the algorithm part. You will randomly select some batch from this mixture. Like for each of the blue square, it will be a tiny batch like this one. And in this batch will be a D by the batch size. And you will compute the covariance of each of the batch. So which means for each of the blue square, it will compute one of the square matrices. You will compute covariance matrices. It's like for each of them, we'll compute a C here. So when you have total like n batches, like n blue squares, you have a total of n covariance matrix. And in this condition, you do joint diagonalization, and you found the transformation that can approximately diagonalize all of them, and the W will impose to be the mixing matrix of this IC problem. And is this part clear?
So it's like you are solving this problem for the observed mixture, but this solution will also work with ground truth.
Actually, observe, yes.
There's a kind of clarity is missing on what the dimension of the covariances and across which dimension you're computing the correlations, right? Because you said every blue square, but you have depth there.
Yeah.
So
Okay.
The dimensions don't match. Like what is the covariance size? D by D? K by
yes,
K? Like
D
what,
by
like,
D. D.
Where does n come from? Is it the number of
N is N is the number of covariance matrices.
Okay.
So which means N
Is that a hyperparameter or is that discovered?
Hyperparameter. This just you can set random.
yeah, hyperparameter.
Okay.
Yes, hyperparameter.
Is this D on the right the same D as on the left?
Yes.
It's
D is the number of components. Then yes. Everything is based on the whole mixture. Even if you select the batch, the dimension doesn't change. It's just the size getting small.
You need another image I wrote to you from ground truth to observed mixture. How do you flatten? Where is the one top somewhere T? You multiply by the mixing matrix. All of that needs to be shown because people who don't know, even people who know ICA superficially will be confused. How do you go from three-dimensional cube two three-dimensional cube by linear mixture.
Okay.
Like linear mixture is a 2x2 matrix multiplied by one dimension, another dimension. So people will confuse it.
Okay.
Just will draw.
I know.
I think on top.
I haven't practiced. I should practice.
No.
If I practice, I can realize the problem. Yeah. Okay. Yes, and I will. So for this idea is based on a theorem.
So can you make all fonts in the entire presentation this small? Yeah. Now I can barely see it finally. Before I just don't read it. It's not cool.
Okay.
All fonts everywhere should be like on that next slide.
Okay. Yes. Okay.
I mean, barely readable now.
Okay.
Before it was like invisible, like beyond the wavelength. So sorry. No. Yeah. You have a lot of space and you're not using it.
Okay.
I left them.
Yes.
Like now,
I will.
Like the perfect composition. Everything is taken. Like there is white space there still unused.
Now the audience can't escape you.
Yeah, you have to just zoom in this a little more. You have white space. Zoom this formula, like make it like this. You have space. You're wasting the space, and you're not making it visible. But yeah, this is a great slide. But in terms of fonts, yeah, make all of them like that. You have the
Yes, I will change the background. So I will just okay.
Yeah, that's easy.
Still, the theorem is joint diagonalization of two batches.
No, you say my theory, because when I'm listening to this, I'm like, this is some grandfather who made this theorem, and Yaorong is just telling us about this theorem. No, this is your theorem, and you're not telling that. It's a miss. It's like, I proved this theorem. I formulated this theorem. You never said that. You say that directly. This is like the only chance in your life when you talk about.
Did I say I found this theory or proved this theory? Or
discovered and proved and formulated, but say this is your theorem, because by default we assume you're talking about somebody else's work.
The easy way to flag that you're the one who stated and proved the theorem is to have the exact formal statement of the theorem, because if you were just referencing it, no one would ever actually do that. But if you're proving it, then you have to state it. And I stated like this, I translated this kind of situation.
Well, he does, right? He states that.
Insufficiently formal.
Insufficiently
formal. I'd like to see a sequence. Or like like the statement on a single line or something.
Well, this for each dimension, if there exist batches, it's formal enough. Then there exists blah 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 is a generalized eigenvector. That's the state. But you need someone.
Yes,
Mike can help you make it look.
Yes, I'm a professional math poser. I can help you figure out how to make the pose.
that's. I mean, actually, I like it. That is true.
Okay. So I discovered a theorem, which is joint diagonalization of two batches may identify one dimension of W. So let's talk it simpler. So for one row of W, so W is the demixing matrix. It's not the mixing one. It's the demixing matrix. So one of the K represent the one row of W. For each of dimension K. Suppose there in this condition there is 5, and if there exists a batch S1, S2, S is from the ground truth, a separated result. If in the batch there exists such batch S1, S2 that their K's component is uncorrelated with all other dimensions. What I mean here, so S1 is one batch of ground truth, S2 is one batch from ground truth, and these are the two correlation matrices of these two batch. And they probably have these features. One of the components uncorrelated to other. But they don't have to be that stronger uncorrelated. I just listed here for more visible, and they should be the same dimension. And in this scenario, if you join diagonalization on this two, not this two, so the relative covariance matrices on the mixture part, it will not look like this one. It will be more mixed. And if you do joint diagonalization on that one, you will get this thing. And the transformation contains the solve of the case row of the matrix W. And this clear. I hope it's clear. Okay.
Hold on a second. Okay,
I think what would help also, since you're verbally trying to say that, is to annotate those two figures. Because I don't know what those figures are.
Yeah,
looking
I
at this
realize.
slide.
Yes.
If you can put, is it a C and a C, or is it a W times C, or what is? If you can,
Yes, I realize.
if you can write here on top of that or on the bottom, what is this? What is that?
Yes.
In this notation, so I can relate this text to this image. But right now, this is something, but I have no idea what it is. All right.
Yes.
Just like visually, I'm looking at like. You kind of, you're saying that, but you're not pointing also, and there's disconnect between. It's very hard to comprehend math.
Yeah,
like that. Right?
I cannot paste everything.
So I would clarify that the batch, when you say if there exists batches, blah blah, that 1 and 2 is what represents the batch. And S is your answer, your ground truth answer that you're trying to find. That's not clear. I wouldn't consider S as the batch. S is your source that you're trying to find.
X is the batch, right?
Yes, actually, yes. For a running algorithm is X. Yeah, this batch.
The batch is from X, not from S. That's what you're saying.
C is from
X. I would suggest instead of 1 and 2, you could say B1, B2, or something like that. If there exists batches B1 and B2 such that the source on those two batches and the covariance of those two batches. So like SB1, SB2.
No, but the statement is that the uncorrelated part will be in the source space, not in the
yes,
not in the mixture space. Mixture will still correlate, but
So is that the notation?
Yeah,
It's
notation
notation.
problem.
Okay.
Maybe you can update it in the paper as well.
Yeah,
for
sure.
Rogers after this.
Okay.
Or call it ground truth batch.
Okay. Okay. A lot of things. And yes, for this kind of uncorrelated components don't have to be only one. It can be exist. Two of these components are uncorrelated, or three, or all of them. Then it will be independent. It will be closely to ICA. But then it's just that we need this kind of feature locally. This feature, there are some correlated components and some uncorrelated components. And for when you do joint diagonalization, they have matched the batches. You will find the relative row of matrix from W. Okay, I will add more notes on this part. So yeah, this I didn't have further proof things to write down in slides of this GDX. And the next part is for the GDRX. But different to GDX, as we select the batch structurally like a small square or any kind of shape, but I use square for simplicity here. But when you're trying to do random batches, GDRX, you will select the batch. Generally, it will be consist by each of the batch is consist by the random pixels, and it will compute a covariance matrix by just a random shaped batch. So in this strategy, it will separate components into super Gaussian distribution. So by by changing this strategy, the objective, it will be, and I try to prove this through one of the objective function. Since you have a lot, let's say one of the matrix D is from the batch. D is the batch covariance of X. And you're trying to do that, you want to make each of this covariance to be to off-diagonal elements to be close to 0, and the diagonal elements to be as high as possible. Generally, this is how the diagonal or geometrically is how the diagonal precise is doing. But when you do joint diagonalization, you're trying to do this precise through a lot of this covariance. But each of the covariance is generated by the random batch from the mixture. So I'm trying to get this objective function. It's about the off-diagonal energy. It's all of the off-diagonal values summation divided by the diagonal energy, all of the diagonal elements through the whole batch. It can be shown that it's something like this. There's this objective function. How should I explain? Yes, JK represent off diagonal when the JJ is represent the diagonal element. So the denominators contains only diagonal, and the numerator contains only off diagonal. And this GDRX precise is trying to minimize this value. Basically, it's to minimize djk square and maximize djj square. And I have the approve of from all of this batch generation all the way to the row. It will be equal to that. Can I say that? Because I didn't include close ones. Okay.
Yeah, and like everything you just said about being maximized over this and minimized over that, that should be in the statement and not necessarily explained verbally.
Mm-hmm.
Yes.
And by trying to prove the row, when you're minimizing this row, I was trying to prove that finally I can prove it. Row will equal to this function, this final equation. And for h of y, I should write down y. Y is the one that I will say wx equals to y. And we will optimize this precise, and finally y will reach to the supposed solution. It's just I will modify this part, but y is supposed to the solution. And so this whole, by minimizing this row, the precise is similar to minimizing this one. It's on the improvement. And for KJK is called a cross cumulance, which has been proved by its common pair from is independent component analysis, a new concept, the famous paper. And it is related to the independence, or more specifically, higher order correlations is kind of called the cross cumulant, and minimizing that will push components to be more independent. And the KJ represent the kurtosis because all of the data has been normalized. Is optimized during a normalized precise, and the CJK represent the covariance. So you can see that the denominator contains Kj, which is a kurtosis. And remember, we mentioned that the row, we're trying to minimize the row, which means we're trying to maximizing the denominator, which means Kj will, I need to mention alpha is a positive integer, just related to batch size and the dimension. So during the training, it will not affect the performance result, and it's positive. So we maximize the denominator, which means the kurtosis of each component will maximize, and also the cross cumulance will going down. And in the meanwhile, the second order correlation will also going down. So by doing GDRX, this precise is trying to minimize cross cumulant, minimize correlation, and maximize kurtosis. And it will try to separate components into a super Gaussian, uncorrelated super Gaussian components. And I proved it as kind of IC like algorithm. It's have a similar results as Informax, but not theoretically same. So this is what GDRX. Yes, I will still modify the notation here.
Anyway, you can chat with Mike about how to formalize theorem on white. slide.
Yeah, I will
In the
modify it first.
Posing.
I will talk to Mike.
Plus.
Well, also, it's just like there's a lot of impedance mismatch between the thing that he says and the thing that's on the thing.
Mhm.
Yeah, like
Yeah.
just notationally, it makes sense. Like everything you're saying makes sense. It's just that the slides should probably just have that information anyway, and so
Or reveal step by step. Another thing to match what you're saying into what we're seeing is only show one formula and explain it. Show the next one, keep it instead of like throwing everything.
Yeah, I get it.
there's no actual restriction on like number of slides you can use to show like your derivation through a theorem. You can actually have like 50 slides here, but it's just so long as what you're saying still semantically matches up with what's on the screen, everything's gonna be okay.
We're taking so long. In 10 minutes, there's like good time out.
Yeah, the difficult part has finished.
If you implement that equation, is that more efficient than your other formulation, original formulation?
But then you have to keep estimating kurtosis.
You mean directly using this one?
Yeah.
But why?
Is it more efficient this way or the way you present?
If it's just linear, this way probably better, faster.
I guess a broader point is like, this is what you did, but what does it mean? The fact that it's minimizing that and maximizing this and then doing so. And so
Oh,
forth.
because there is a joint diagonalization.
Uh-huh.
So it's all the way point here. I'm not trying to deliver this objective function, but by joint diagonalization is similar to minimizing this objective. There's a point, and this one indeed can be applied to further like self-supervised learning. Or you want to do anything that want them independent, you can try and
I'm
apply.
just trying to gauge if there is even like, if your answer were like this is not as efficient as what I'm implementing, your original definition of row without other simplifications, then that's, in my perspective, another point to bring up that my implementation, this original formulation, is a more efficient implementation, and it gives you that as a bonus,
But
without having to go.
I'm not exactly sure exactly this equation, because what I tried using kurtosis plus this cross cumulus. Cross cumulus divided by kurtosis something or minus, and it's faster.
So you're never computing kurtosis, right?
In your current one, you're not computing kurtosis.
No, current one.
And you started from just second order. And
It
you
is
ended on
just
kurtosis, so you're getting kurtosis for free.
Oh, it's dry because when you're trying to minimize, you're trying to make the off diagonal close to 0, it will be squared. And also, if you the diagonal part is to be squared because the whole matrix element is squared.
I mean, that's part of the discovery is what I'm trying to say.
Okay.
You started from a purely second order method and you got fourth order. For free.
So it's not acceptable.
It's great. It's good involved.
Okay. How to put it? How I derived it?
No. I mean, just to say this is a benefit.
Oh, okay. I get it. Yeah. Okay.
If that's true.
But the thing is, it's like, okay, we discovered that this approach produces independent components. And then we came up with this proof to figure out what is it doing, why is it producing independent components. And the way you sound to me is like nobody publishes negative results kind of thing. It's putting first deriving the answer and then like, okay, now I will pretend that I first derived the theory and then came up with an algorithm. But this is not the case, right? So it's not that we knew the theory and theory guided the algorithms. It's more realistic. The practice guided the theory. So that's how it happens here. Yeah, we can tell the story two ways, but it will not be true. This is the theory. in theory resulted in something not this happen. But I know it doesn't matter what happened. No, well, at least, yeah. This is just an attempt to understand why the algorithm works and like a plausible explanation of what works. But your doubt is like, okay, well,
There's no doubt. I'm supporting.
no. You don't have to support. Yeah. You don't have to. Yeah. But like that, I think the question is valid, right? Is this if minimizing this formulation gets us independence, why are you even using your algorithms? Why don't you? That's how I heard that was. Yeah, but like, why don't you just like? Well, but that was my question. Mike's question for sure.
If this is more expensive to compute than the thing you're computing right now, then
yeah, mention
it's
that.
annoying
Like, is
that-
it more expensive? I don't think so. Right?
It's
We're
definitely-
out of
it's
time
definitely-
for people online or watching this. So sorry, you don't have to stick around if you have to go. But I don't know how many slides do you have. It's
just experiments and further.
quickly show us the experiments. So at least yeah.
Yeah.
But
And
again,
some experiments that are just skip it. And for some, there's a kind of experiment from for data set, mixture from 5 components all the way to 100 components, 5, 10, 15. And this is a result from some sample.
no, we know the ground truth exactly here. That's the point, right? That's
Yeah.
the point of those experiments. And see how much white space you have there. If you've used it, we would have seen the images. But right now the images are tiny, and
Yeah.
you're not bringing
Okay.
our attention to that. Like, are those mixtures or are those results? Ground truth. Yeah. Like that. Make if you make this whole image.
Yeah.
Like, move this word over here, make it occupy the entire thing, and then you can point us to like ground truth, the result. What is the mixture? There's no mixture, right? Those are just the results.
Yes.
Oh, okay. Well, but then you can point to us. Those are the resulting components. Look how messy they are. Look how messy they are. Well, this one is good. This one is good. This one is good. This one maybe yeah. So just like
Okay.
you show this. Have a slide. You don't give us time to understand what's on it, and you jump here. You're like, well, then don't show it if you don't want to talk about it. It's something like that.
Mhm.
Or show it large so we can see and point to key points. All of the results from other methods are messy, but those 2 methods are clear, or something like that. Just
Okay.
oh. Concrete, every method is perfect. Doodle, every method is. Besides ICA EVM is perfect, or something like that. Just point
Mhm.
the listeners to that.
Yes. Okay, got it. And also experiments on FMI.
No, go back. Tell us that JDX is the fastest method. It gets us the best correlation, best. Higher is better, lower is better. We are at the lowest point when lower is better. Where are they? Just tell that. Otherwise, it's like, those are box plots. You know what box plot is? It's that. Next. Like, what's the point?
Okay. So this is our experiments on the 4 data set. Experiment based on 5 components all the way to 100 components. And for left is at least some sample result from different data sets. And you can see that for the jellyfish, that the GDX and all this combined is I plus covariance matrix with I didn't measure because it's on the experiment setup part. I have random batch and the structure batch. I put them together. It's sometimes good at like solving the doodle images. This is why I have this combined here. And you can, but still let's start from the jellyfish. And you can see the separation quality of a GDX and the combined result is just nearly perfect as ground truth. But all the other methods are just messed up because GDX is kind of an IC algorithm. If you push them to be uncorrelated, you cannot separate some components. They are highly correlated to each other. and a similar thing to the enemy data, and also see the histogram. For the IC algorithm, they're trying to separate them to some super Gaussian or sub Gaussian. Even for fast IC, it's good at separating super Gaussian, sub Gaussian, but they assumed strictly push the data subcomponents into uncorrelated. It will not found in the histogram, the distribution of the data like that. But they can see GDX and the combined GDX one can relatively nearly perfectly capture the distribution of it. And also for the congruent data, everyone is good on that because it's independent super Gaussian components for all of the data set. So everyone is good at it. For GDX, it still can separate it. It doesn't care about the distribution, doesn't care if it's independent or not. As for the doodle data, this is one case that the GDX probably relatively has some bad performance because of the structures are less captured. You can see the histogram is just a pause-like distribution. So it will, but it can still capture relatively good components. And I cannot list more components of that, but the GDX do have some of them are super perfect, but some of them do messed up because I want to do comparison of everything together. But I combine with GDRX and GDX together on separating this one. It will capture the structure because the GDRX put some trade-off on the GDX by trying to find the super Gaussian distribution. All the pause like is to super Gaussian distribution, and all the other methods are, well, Informax can also capture this pause like distribution. So only these two methods has super the extreme best performance on the doodle data, but GDR acceptable. Fast IC extended Informax, but IC EVM is based on some well, yeah, I will not talk about that. It's not the perform the well on the because I'm not very familiar on this algorithm. It's just it's good at separating.
I'll ask you a question about.
Yeah.
Prepare.
Yes, I know it can separate the different kind of super sub-Gaussian distribution based on some bounded entropy estimation. I just don't know exactly how it's optimized, but it can be failed on this extreme case. And for the box plot, I listed the armory distance and the correlation and also the computation time. So the armory distance, you can see from the it's too small. I cannot see it even here. For the GDX and the three blue, light blue.
It's for now because we have to fast say.
Yeah.
We're always better.
Yes, always are for the lower.
In all of the three metrics.
Yeah, lower armories
and
higher
move
growth.
on to the next slide and wrap up this.
Yeah. Okay. For the experiments of fMRI data, I do group IC applied on F1 data set. And the components are selected based on the alignment with Newmark template. And you can see the result from Informax and the GDX have a lot of aligned components, but not all of them. And even if they capture very similar components, one of the components I really want to show is 52. Like you can see, they capture very similar shapes, but for Informax, because of this property of this algorithm, is we're trying to find the highlighted points, highlighted voxels from these images. So you can see there are strong highlighted parts from this selected network. As for GDX, we're trying to extract the shape of it. So actually, it cannot capture the highlighted voxels. Instead, it will trying to capture where, because fMRI is very noise data. GDX in this condition will trying to capture this kind of shape or activate blobs there. So it will not that highlighted, not contain that much highlighted points, but it will still capture the shape. So what I want to state is that GDX will still extract the network, but based on a different strategy. It's not trying to find the super Gaussian, some very active points, but the active region in an approximate way. So, but by another thing is that when I trying to evaluate which of this result is better, I'm trying to using the extracted networks to do back to reconstruct the FNC functional network connective of each of the subject, and by using the FNCs, we do the okay. I think I didn't crop the title, but anyway, the FNCs are the average from house control minus asthenias patients. And I use all of the 311 subjects of FNCs to do classification test. So here are 3 test results from Informax, GDX, and Neuromarks. And you can see that the result of GDX is almost better than, and scan for logic regression can achieve near 90% sometimes. And yeah, and that's the experiment for FMS, and some more stretch goals. And I'm prepared for self-supervised learning application by batching strategy. So there are some of the SSL methods to some redundance reduction or contrastive learning. They kind of compare or augmented or the positive and negative samples. They're trying to compare the similarity between the samples or learned representations. Like for here, I want to compare more with the Bartle twins because it has a more similar strategy. What Bartle twins doing is it will throw the data into a network and learn a representation dimension, let's say 100. And they want trying to make the 100 latent to be independent to each other. But in Bartle twins, they're just using second orders just to compare the correlation between this learned latents. So it's just second order. But based on GDRX, the second order statistic can be reflect the higher order statistics, and which means this can make the latent to be more independent instead of just uncorrelated. So I was trying to change the Bartle twins objective to the GDRX objective and test it on the image at 100. And as indeed outperform the Bartle twins. Like for top one have 4% increase. And also for top 5 has a 2% increase. So then I'm thinking this one can be implemented further or some and submitted to conference recently. Yeah, I put this image here. Okay, let's skip. And spectrum reconstruction, yes, for the spectrum, they are independent, but the correlative spectrum, we have there's a observed a mixture of HIC data, and they can put it to the work can be combined with GDX, probably can help learn the spectrum from the mixture. And also the federated GDX, because based on the feature of GDX is only needs covariance of sub-batches. So probably can apply to a federated way, like we have a group of data, we just can collect it the same location of covariance matrices and apply GDX. And it can help do privacy protection and data sharing stuff. And conclusion, and thank you. Thank you.